All right, so now we're going to switch gears. Instead of talking about preparation of alcohols, which is what we've been doing with reduction and Grignard reactions, we're going to be talking about reactions of alcohols, so treating them as starting materials. We've seen reactions of alcohols a fair amount, so let's do a bit of review. All right, the first one is, let's say I've got an alcohol like this. So this would be tertbutanol. And I want to change this to an alkyl halide. What reagent should I use? HBr. HBr? Okay. Is this going to be an SN1 or an SN2 reaction? SN1, right? First step would be protonating that alcohol. It'd be a good leaving group. It'd fall off, form a stable carbocation, and then bromide can attack in. So this is review from first term, but this is a classic SN1 reaction. What's a pitfall with this, though? Are there any pitfalls? So under certain circumstances, SN1 reactions are in competition with E1 reactions. However, in this situation, bromide's a really, really, really crummy base, so it's not likely that it's going to be in competition with E1. All right, let's take a different example. Let's say I have this compound, and I want to make it into an alkyl bromide. What should I use? So you could use HBr. So if you use HBr, you could do this as an SN2 mechanism, right? So protonate that alcohol, make it a good leaving group, but then the bromide would attack the backside and kick off water. So it is a different mechanism. There's also a different route, though, besides using HBr. Does anybody remember that? If we're not protonating our alcohol, what should we do? What's that? So we need to convert this to a better leaving group. Tosylation, right? So tosyl chloride in the first step, and then we need to kick it off with our nucleophile in the second step. So both of these could be used. They're both SN2 reaction mechanisms, though, right? The key thing is remembering when the mechanism's SN1 or SN2. All right, there was one other way to do this, where you can convert an alcohol to an alkyl halide with a chlorine on it. This is a little bit harder. You have a few options, just like with the top one. You can either treat it with HCl. However, if you treat it with HCl, you actually need a catalyst to help it work. You need zinc chloride. And I'm going to put a little circle around this and indicate that this is a catalyst. That allows this to do an SN2 reaction a lot more easily. Just using HCl on its own won't accomplish this transformation. Alternatively, like we saw, we can use tosyl chloride. Oh, I should put pyridine in both of these too. We need a base. Followed by sodium chloride. And I'm also going to put a little note on this catalyst. This only works for water-soluble alcohols. So it is fairly limited. That's a good point. So small alcohols, meaning they don't have very many carbons on them, tend to be water-soluble, right? Because the main intermolecular force for them is H bonding. But if you have a really, really long alcohol, like let's say 1-decanol or something like that, dodecanol, then it's not going to be very water soluble, because then there's a lot of greasiness on it, so to speak. So this really only works for water soluble small alcohols. Both of these are SN2 reactions, though. All right, so these ones work pretty well under a lot of circumstances. However, you can see with HBr or HCl, you're using a really, really strong acid. You may have other functional groups in your compound that react with the strong acid. So let's say up here, right, we've got an alkene somewhere else in our molecule. If we treat it with HBr, the HBr could also react with that alkene. It prevents us from doing some of these simple transformations. The problem with tosylation is it's really not very green. There's a high atom economy, but there's also some other workarounds that we can use besides just tosylation and accomplish it in one step. So let's take a look at some new reactions. All right, in the new method, we can accomplish this pretty easily. We can go directly to the alkyl halide with chlorine on there, and we've got to use a reagent SOCl2. This is thionyl chloride and pyridine. Or, nope, it's one step, which, and compared to the tosylation, trims down the amount of work you have to do, right? Or if we want to, we can change this to the bromide using PBr3, Phosphorus Tribromide. So these are two really nice reactions. They have higher atom economy than the tosylation. They don't require multiple steps, and then you don't have to worry about the unwanted acid chemistry if you use HBr or HCl. All right, so I did want to make a note that both are SN2. What does that mean if you have a stereocenter? Yeah, so we would invert any stereochemistry. All right, yeah.
And so this works for the longer chain of alcohols too?
Yes, this works for practically any alcohol. Yep, great.
What about diols?
It'll work with diols. You can't really selectively favor one alcohol on a diol over the other, so chances are it'll do both. Yeah. All right, so let's take a look at the first mechanism with thionyl chloride. All right, this is a pretty long mechanism, but bear with me. Thionyl chloride is super, super duper reactive. It's not one of my favorite reagents to work with. It'll react with air in the room because air has moisture in it, so it's kind of a pain. But just like what we saw last term, the problem with this is alcohols are a bad leaving group. So the main goal with this reaction, just like with tosylation, is to turn that bad leaving group into a good leaving group. Okay, so we've got lone pairs on our alcohol. The sulfur in thionyl chloride is really, really reactive. Does anybody know why? Yeah, it's got a huge amount of electron density being pulled away on every side. And there's a resonance structure where you can move electrons up to that oxygen, giving it a full formal charge. So in this case, the lone pair is going to attack into that sulfur and kick up electrons onto the oxygen. We're going to have an oxygen with a positive charge at this point. We're going to have the sulfur still bonded to that oxygen, but this oxygen coming off the sulfur will now have a negative charge. And then we'll have two chlorines coming off of it. This is really reactive. There's no way you're going to be able to isolate this, at least not in a normal lab. So this negative charge is going to clamp down and kick off the best leaving group that's available, which is going to be a chlorine. Oops. All right, so chloride's been kicked off now. That's our leaving group. It's actually an important leaving group because it's going to participate in some of the next steps. But before we can do the next step, we need to deprotonate our oxygen. And that's where the pyridine comes in. And if you remember way back to last term, pyridine is an aromatic heterocycle. It's a really nice base because it's not a very good nucleophile. So in this case, the pyridine is going to steal the proton coming off of that oxygen and get us to our neutral species. And we still have our chloride floating around, which is pretty important in this step. All right, so now when we look at this, this new chunk that we've installed on here is a really good leaving group. All right, chloride we know is a decent nucleophile. And is it a better nucleophile in a protic solvent or an aprotic solvent? Aprotic solvent, which in this case, pyridine is actually going to be our solvent. Pyridine isn't protic, so chloride's going to be a pretty good nucleophile. So it's going to do an SN2 attack on the backside of this carbon and kick off that leaving group. But the way this leaving group gets kicked off is really cool, in my opinion. When this happens, this bond is going to break. It's going to clamp down, form a new double bond, and cascade off and kick off the chlorine. So it's kind of like a domino. Yeah. All right. So this is where the SN2 reaction takes place, right? So we're doing that backside attack. We're kicking off our leaving group. If we had a stereocenter, we would invert it. Okay. The cool thing is, right, we kicked off chlorine. So that's going to be one of our leaving groups. And then the other chunk, we're forming a new bond, or at least a new double bond between oxygen and sulfur. And then we've got another double bond on the other side. The reason that this works so well is sulfur dioxide, the thing we kicked off, is a gas, and it will actually bubble out of solution and help drive the reaction to completion. And then our countercation in this case is going to be our protonated pyridine. So we should account for that if we want to include all of our byproducts for this reaction. Does that make sense? I know it's kind of complicated, but in general, if you have a leaving group that falls off and becomes a gas, that is a phenomenally good leaving group. That's the power of this reaction, is that gas formation. All right. Any questions on this one? All right. There's a few other reagents that work well besides thionyl chloride. The Klein textbook really latches onto this one. If you read other textbooks, there's like 5 other reagents that are kind of similar. We're just going to stick with this one for right now. All right, let's do the mechanism with PBr3. What's that?
Is this a turn-the-page mechanism, or is it like...
This one's shorter.
Oh.
Yeah. It's not one step. All right, so phosphorus tribromide is also super duper reactive. It's not the easiest reagent to work with, but same idea. You have a bad leaving group. And we need to change this bad leaving group into a good leaving group. So just like before, we saw sulfur was really reactive due to all the electron withdrawing features that were attached to it. In this case, it's got bromines coming off, the phosphorus does. So this oxygen will actually hit that phosphorus and kick off a bromine. And then we have Br minus floating around. The weird thing with this one is you don't even need a base, because at this point, this is a really good leaving group all on its own. So in this next step, because that's a good leaving group, just like before, your anion can attack the backside and then just kick electrons up to that oxygen. And we can get our alkyl halide plus our phosphorus byproduct. So this mechanism is a bit easier, but just like before, it's an SN2 reaction. So if we have a stereocenter, it's going to get inverted during this process. Does that make sense? All right, so just more tools for the toolbox. If you want to add this to your reaction map, go for it. As we go through the year, I've had students that will remake the reaction map like every week and add all the new reactions to it. It's a good way of reviewing all of your mechanisms and just having a big picture view. Like I said, when we made our reaction maps, there's not always one right route you can take to interconvert functional groups, just like we saw here. So sometimes you might need to have multiple options available. Yep. Yeah. All right, so we've done substitution reactions with alcohols, both last term and now a few new ones this term. We need to switch gears and talk about elimination reactions, but I'm going to just really briefly do that. Because again, yeah.
So on the other one with the chlorine, when we grab the, on the final step, when we kicked off the leaving group, another chlorine came off.
Yep.
Why didn't another bromine come off and make a double bond?
Yeah, so the oxygen in this one has a positive charge, which means it's a good leaving group. I have had students ask, well, why in this one doesn't the chlorine attack this intermediate right here and do a similar mechanism? If it does that, you're not going to form sulfur dioxide gas, so it's not as favorable. So we need to deprotonate that oxygen first. That way, in the subsequent step, you form sulfur dioxide. Yeah.
So if you don't use pyridine, so you don't have that base, this reaction would still happen. It just wouldn't bubble out as a gas. It could be a different byproduct.
That's a good question. I honestly don't know if the reaction would work if you don't have a base. I believe you need some sort of weak base around to help drive it to completion. Yep. Yep. Yeah, and that's your solvent. So it's kind of a 2-in-1 combo. All right, so elimination reactions. I am going to tell you to review Chapter 8 if needed. We just don't have enough time to go back and review all of our first term chemistry. But really quickly, we'll take a look at a couple of these. Let's say I have this alcohol and I want to convert it to an alkene. What reagent do I need? Do we need base? It's not a good leaving group. We need acid, right? Do we need catalytic acid or what type of acid? Dilute acid, concentrated acid, cold, hot, looking east? Catalytic acid. We don't want water around, right? Because we saw if we have excess water around, meaning our acids dilute, we actually favor the alcohol over the alkene, right? So we would do the reverse reaction if we had dilute acid. All right, do we want it hot or cold? Hot. Is this an E1 or an E2 reaction? E1. There we go. Because we can form a stable carbocation, this is most likely going to be an E1 mechanism. All right, let's say, on the other hand, I've got this alcohol, and I want to make an alkene from this alcohol. Am I going to be able to form a stable carbocation? No. So it's unlikely that it's going to do E1 chemistry. So what's another route? E2? How can we do an E2 reaction? Can we just throw a base at it? So if we threw a big base at this, what would happen is we'd deprotonate the alcohol and it would look at you and it wouldn't do anything more. Tosylation. Yeah, we need to change it into a better leaving group. So we'll do tosyl chloride and pyridine in that first step, or we could have used thionyl chloride, or we could have used PBr3. Any of those three options would work. I'm just throwing out the one we're most familiar with. And then, what do we need for step 2 once we convert that alcohol to a good leaving group? A good base? Can I use sodium hydroxide? No, otherwise we'll just reform our alcohol. So we need a non-nucleophilic base. What's a good non-nucleophilic base? DBU, DBN, sodium hydride, potassium terbutoxide, one of those ones. So we'll just pick one. We'll say DBU. Why not? All right, so this is just review of last term chemistry. The key thing to remember is this must be non-nucleophilic. All right, so now the last chunk of the chapter, oxidation of alcohols. So let's say we've got this alcohol here. What we can do is we can convert this directly to a ketone. Would this be an oxidation or a reduction? So if we look at this carbon right here, it has 4 electrons minus 4, will be an oxidation number of 0. And then over here, this oxygen would be 4 minus 2, would be positive 2. So it looks like we lost 2 electrons going from our alcohol to our ketone, right? So this must have been an oxidation because it lost 2 electrons. Conversely, we saw we could go the other direction, which was reduction, where we gained 2 electrons. All right, what reagent would we need to do the reduction of the ketone to the alcohol? So what I mean is, what reagents would we need for that backwards arrow? Sodium borohydride and an alcohol, or we could use lithium aluminum hydride followed by some sort of workup with a weak acid. What we're going to be focusing on today is that top route. So how do we do the reverse one? How do we go from the alcohol all the way to the ketone? So let's take a look at primary alcohols and then we'll go from there. All right, so let's say we've got a primary alcohol. Looks like this. We know that a primary alcohol would only be bonded to 1 carbon, so it would have to have 2 hydrogens on the outside. What would the oxidation state be for that central carbon? It'd be -1. So the carbon attached to that alcohol would have an oxidation state of -1. And during an oxidation reaction, you can essentially think of it as a loss of hydrogen and its electrons. So we'll say oxidation. And if we lose one of those, we could form an aldehyde. And that aldehyde, the carbon in there would have an oxidation state of +1. So this would be a 2-electron oxidation. We can accomplish this with a wide variety of reagents that we'll talk about next. But the weird thing with this is you can continue to oxidize this. And if you oxidize it and remove that last hydrogen, you can convert this all the way to a carboxylic acid. And this has an oxidation state of +3 for that central carbon. All right, so primary alcohols can actually undergo 2 separate oxidations. If we have a gentle oxidant, we can stop at the aldehyde. If we have a really, really strong oxidant, it will blow past the aldehyde and go straight to the carboxylic acid. So we do need to be careful with what reagents we choose. All right, secondary alcohols. Let's take a look at what happens with that. All right, so with a secondary alcohol, we only have 1 assumed hydrogen coming off that central carbon. And the oxidation state for that central carbon, for this example, would just be 0. All right, so if we go ahead and we try to oxidize this, we can remove that hydrogen and we can form a ketone. The oxidation state at this point will be an oxidation state of +2 for that carbon. Can we oxidize this any further? No, we don't have any other hydrogens coming off that central carbon. So no oxidation is possible beyond the ketone using simple oxidation chemistry. All right, let's do the last one. Tertiary alcohols. All right, so for a tertiary alcohol, it would look like this. Whoops, let me clean this line up. What would happen if we oxidized it? Nothing. It doesn't even have a hydrogen, so no reaction. So tertiary alcohols are completely unreactive when it comes to oxidation chemistry. All right, so that's an important thing to remember. Students oftentimes get confused and they try to draw some sort of ketone with the Texas carbon. That's not a real thing, so avoid that. All right, so now the question is, if we're only dealing with these primary and secondary alcohols, what sort of oxidant do we need to accomplish each of these reaction arrows? I just put ox in a box. That doesn't really help anything. Dr. Seuss. I've been called Mr. Rogers this morning and Dr. Seuss. I don't know what's going on. All right, so let's take a look at the oxidizing agents. Those of you that have been in lab, I've told you about the fun nature of chromium. What's fun about it? It's toxic. It'll give you cancer. So these reactions, while I'm showing them to you, they're really, really old school reactions that most chemists prefer to avoid because chromium 6 in particular, is really nasty and can cause leukemia. However, in the 1950s, this was really cutting edge. They would take chromium trioxide and then they'd mix it up with sulfuric acid and acetone. And by doing that, they can make chromic acid. That still will give you cancer. I don't know what type. It'll give you an acid burn and cancer, just to add insult to injury. All right, so that's one way of doing this. Oftentimes, you'll just see CrO3 listed in addition to all these other reagents, and you should immediately think this is just a way of mixing things together to make chromic acid in solution. You can't just buy chromic acid in a bottle. You normally make it as you need it. All right, the other reagent is pretty similar, also highly toxic. Draw this 10 times fast. There was a lot of, I'll be honest, pure ignorance regarding the health and hazards associated with these compounds. I'll try to pull up a paper later, but one paper, it's kind of upsetting. A chemist was writing about all this research they did. I can't even remember what sort of chemistry they were doing. And then the footnote in the paper was something along the lines of, it should be noted that this reaction is quite hazardous. 3 of the chemists that worked on this paper have subsequently died. People just didn't know back then how bad this stuff was. But this is sodium dichromate, which can be abbreviated Na2Cr2O7. And again, you need sulfuric acid. And water. These aren't, I would say, acutely harmful. They won't kill you in one step. However, they're not super safe either. Yeah. Yeah. All right. So this is a really, really strong oxidizer. And it's toxic. Those are the 2 main things to remember about chromic acid. It's a really, really, really strong oxidizer. In fact, it can do a lot of different oxidation chemistry beyond what I'm showing you right now. All right, so let's take a look at chromic acid as a strong oxidizer. Okay, so let's say we've got this alcohol, one you're hopefully familiar with at this point. So cyclohexanol. If we treat this with an oxidant, so let's say we use Na2Cr2O7 and H2SO4 and water, what we will do is a 2-electron oxidation, and we can convert that directly to the ketone. So in this case, we went from a secondary alcohol to a ketone. Alternatively, we could have used chromium trioxide, sulfuric acid, and acetone. It would have done the exact same thing. All right, so pretty straightforward, strong oxidant. We can't oxidize past the ketone because we don't have any more hydrogens coming off the carbon at that point. All right, let's take a look at a separate example. Yeah. I'll show you the mechanism. It's kind of hand wavy though, so bear with me on it. We'll get there. That's what you want to hear? Magic. All right. So in this example, we'll start with the primary alcohol. And we'll use that same reagent. We'll use Na2Cr2O7, H2SO4, and H2O. And if we think about ripping off one of those one of the hydrogens, what do you think we'll make? An aldehyde, right? All right, so this is our aldehyde. The problem with this is so strong you cannot isolate the aldehyde. What do you think our final product is actually going to turn into? Carboxylic acid. So it's uncontrollable for primary alcohols. You'll go straight to your carboxylic acid. All right, the oxidant in this case is way, way too strong to stop at the aldehyde, but I'll show you a more gentle oxidant later. So getting back to Ali's point, what is the mechanism of this? All right, this is one of the mechanisms, I'll be honest. The Klein textbook does a really poor job of explaining, but I'm still going to show you the way he shows it. It's a lot more complicated, and to be perfectly honest, more complicated than we need to know for this course. All right, so let's say we have the secondary alcohol, and we've concocted chromic acid by mixing up our reagents that I showed you before. What this will do is form something called a chromate ester in equilibrium. All right, and then in solution, you typically have water around. Yeah, so this is where the hand wavy part comes in. He doesn't really explain how the chromate ester is formed. He just says it's in equilibrium and it gets formed. We're not going to really get into that. All right, anyways. So at this point, we have... So we've lost this alcohol in the process. Yeah. Yep, we've lost an OH and an H, meaning there's water floating around, right? All right, so this water that's floating around is going to actually grab that hydrogen. It's going to clamp down, and it's going to kick off your chromium. So you can convert this to a ketone, plus your chromium byproduct waste, super nasty stuff, expensive to get rid of, will cause cancer. All right, so this is the short and simple mechanism of this transformation. The reality is that first equilibrium step is obviously a lot more involved than they're showing here, but we're going to leave it like this for right now. All right, so now going backwards. We talked about this mechanism. Up here, we said that we cannot isolate the aldehyde because our oxidant was too strong. So a simple solution is find an oxidant that's a little bit weaker, one that's gentle enough to stop at the aldehyde, but isn't so strong that it overshoots and goes to the carboxylic acid. So let's take a look at the gentle oxidizers. And these gentle oxidizers will avoid overshooting to a carboxylic acid, and it'll work with primary alcohols or secondary alcohols, which is pretty nice. So the main one that you'll see in our textbook is Pyridinium Chlorochromate. And this is usually abbreviated as PCC. It's just a lot easier to write out. So if you're trying to write this for a reaction, you can just write PCC above the reaction arrow and I'll know exactly what you're talking about. So will any other chemist on the planet, hopefully. Maybe not inorganic chemists, but they're not very helpful anyways. All right, so to make pyridinium chlorochromate, first you need pyridine. Then you need chromium trioxide. And you need HCl. Again, we're using this nasty chromium. But when you mix this all together, the pyridine is going to react with your HCl and form this cation. That's the pyridinium part. So it's the cationic species. And then your chlorine is actually going to react with the chromium to give you this ion called the chlorochromate anion. So this is really the business part of PCC. All right, so I'll show you the cool thing that you can do with this. So if we take that same example that we did previously, oops, sorry, this should be an alcohol. Where you have a primary alcohol. You can react this with PCC, and you can stop at the aldehyde. Conversely, if you use a secondary alcohol, and you react this with PCC, what do you think you'll make? A ketone. In this case, you'll just make acetone. We don't have to use PCC for that oxidation of the secondary alcohol. We can pick. So we can use PCC or we can use chromic acid. Either or will work. Yep.
If you have an excessive amount of PCC, will it go past the aldehyde to a carboxylic acid, or is it just not strong enough?
So PCC is not strong enough to make carboxylic acid. Yeah. So let's make a note here. You can also use chromic acid. All right. In the third edition of the textbook, how many of you have the third edition, first of all? Looks like maybe 20% of the class has the third edition. If you read through the third edition, one really nice addition that he included was alternatives to these chromium-based oxidizing agents that are much more environmentally friendly and won't give you cancer. All right, so let's take a look at some of these. Yep.
So these are gentle green ones, are they strong green ones, or is that kind of?
Yes, I mean, you could pull up a book on oxidizers and probably find 1,200 different mechanisms that will do things. I'm just going to show the most common ones that you'll run into. All right, so the first one is called the Swern oxidation. And the Swern oxidation will work really similarly to PCC. I'm not going to do the whole mechanism for this, but the main thing is you need something like TFA or some other acid source. The one that they use in the book is oxalyl chloride, so COCl2. Then you need DMSO, and then you need dichloromethane typically. And you have to run this very, very, very cold, like almost dry ice conditions in order for this to work. But really, it'll do the same reaction as PCC, so what will we make? We'll make an aldehyde. So just like PCC, this will stop at the aldehyde. I was telling somebody in the hall that the byproduct of this reaction is dimethyl sulfide. This stuff stinks to high heaven, so you know the reaction works when you can clear a room out. All right, the mechanism, if you go through OneNote, I've got a full detailed mechanism. It's pretty complicated, so it's not something I'm going to expect you to know. If you want, you can even write Swern above your reaction arrow and avoid having to write out all of these things. I'm fine with that too. All right, the next one is Des-Martin periodinane. I'll write it down. Okay, and we'll use the same alcohol. Like I said, both of these are really similar to PCC in terms of their reactivity. And people just abbreviate this as DMP. The structure is fairly complicated. It's a bicyclic ring system with a bunch of hypervalent iodines on there, which makes it a very strong oxidant. And same thing. We can stop at the aldehyde. All right, so looking at these, I have had students say, well, these seem awesome. They don't cause cancer. You mentioned the downside to the top one is that this is stinky. Oops. No, the second one's actually more complicated than that. It's not stinky, it doesn't cause cancer, but it's explosive. So usually what you see chemists doing is some sort of variant of the Swern oxidation. That's the most popular one even today. And even with the Swern oxidation, I think there's like 5 different variations on it where you can use different reagents and it still accomplishes the same thing. All right, like I said, if you're interested in seeing the mechanisms for each of these, I put them on here. It goes into a lot more detail than the textbook. In fact, I pulled it from an advanced chemistry textbook. You can see why we didn't cover this in class. But this is the DMP reagent. It's hypervalent iodine, but like I said, it's quite explosive, and you can see the reaction's a lot more simple for that one. The last part of the chapter is oxidation of phenols and bioredox reactions. If you want to, you can watch the Khan Academy video, but it's not going to be anything that I'm going to test you on. It's not synthetically that useful, but if you are taking biochemistry, it's kind of interesting. So those of you going on to biochemistry, it's worth a watch. All right, that's where we'll stop today. Study session tomorrow at 1:30 in this room.